Okay, this is Physics25DBlake. It's the chapter review for chapter 5. We're at the end of week 2.5. And in this problem, you have to calculate network. Now, there might be a simpler way to do this. I'll find that out in the future, I guess, but kind of in a hurry here. The mass is 8,000 kilograms. And by the way, I'm converting all those scientific notations to this, and that's probably screwing up my significant figures, so there's not probably right significant figures on any of these. Acceleration is 1 meter per second squared, and it's a height of 30 meters. This is probably the hardest problem of all of the ones here, actually, because it's network and that's confusing. So you got an airplane designed for vertical takeoff, and what you want to do is calculate this network. So this may not be the shortest way to do it, but it's probably the most intuitive. I'm figuring out, okay, the airplane is applying force through a distance to do an applied work up, which is greater than its gravity, force of gravity, which is its weight down. And the leftover is net work. So if I add this one, which is positive, to this one, which is negative, I'll get the net work. And instead of calling it a driving force this time, and then I'm going to call it a applied force, driving force, applied force. In this context, it'd be the same thing in this problem. So if you've got a net force, you add up your forces and you get a net. I'm supposed to add this one, aren't I? In this case, I've added as a negative. That is going to be easier. It's going to be, because they're opposites. Just add it as a negative, subtract it. Take that to the other side, so your gravity and your net are going to be, this applied force is going to have to, basically, if there was no gravity, it would take off at 10.81 meters per second squared. But gravity is going to eat up 9.8 meters per second squared to that, all but a meter per second squared. So you multiply your 8,000 times 10.81, your net force, or your applied force, your driving force, in this case that's the same thing, is 86,480 newtons. Now, so I'm going to apply that 86,480 newtons through 30 meters. Whoops. And then subtract off the work done by gravity. And it comes out to be 2.4 times 10 to the 5th joules. Now, the one little thing I did forget is this time, maybe I should have done it differently. I was going to put the 9.81 in here as a negative, and I forgot. Well, I tell you what, to make it consistent with what we did the first time, why don't I go ahead and put my negative instead of here, out here, like so. There we go. So then I have an applied work done by the applied force, and I'm subtracting off the work done by gravity, and I end up with net, and that comes out to be 2.4 times 10 to the 5th joules. I think there's a way to shorten this up, but it's probably more intuitive this way. You take your forces to get a net, say, well, this one must be gravity plus the net, or my force must be gravity plus the net, and you apply that force through this distance and just subtract off the work done by gravity, and that's the leftover. That's probably the most intuitive way to do it. Okay, now, 21, I like this question. I've never successfully pole vaulted anything significant, but it gives us a chance to talk about work in a, it says discuss the energy transformations that occur during the pole vault event. Disregard rotational motion and air resistance. So you start off, you know, back when you're getting ready to pole vault with chemical potential energy, and you're going to burn, you know, a couple of calories maybe doing this thing. And you start running and you get a kinetic energy. You do work and you reach a maximum kinetic energy. But if from that point when your pole hits the ground you just stop, you just coasted from there, you wouldn't get nearly as high as what they actually do. Because what they do, once that pole hits the ground, the good pole vaulters, that pole's going to start to bend. Well, while that pole is bending, they're driving, doing work, pushing force into that pole, storing energy. So not only were you running fast, now you bent the pole by pushing in there farther. And then you jump up, going to add some work there, and then the pole's going to go up. And then at that point, you're upside down, pushing against the pole, pushing upward, getting your center of getting your legs over. Your center of mass actually passes under the bar. Get your legs over the body and then flipping and raising your arms over. And so you've added a great deal of work just beyond your running speed by pushing that pole to bend it, by jumping, and when you're upside down, pushing off the pole. All those things together add quite a bit more distance. Okay, so to sum that up, you know, basically you're starting with, you've got kinetic energy when you're running, but you're also got elastic potential energy you're adding in this spring, or, well, it's a spring really, it's at the pole, but you're treating it like a spring. And then when you go over, you've got gravitational potential energy up here. Okay, next one is 27, a child in a sled. This one's pretty easy. You can do this one. Going down a hill. So the hill is mgh. Kinetic energy is 1/2 mv squared. Doesn't matter the mass. Shouldn't matter very much like in a bobsled where you put the mass or anything like that. Mass cancels. You just got g times h equals 1/2 v squared. You know you're going 12 meters per second. It works out to 7.34 meters. Yeah, sounds right. Okay, let's go on to the next one, which is, I can't see, did I do this one differently? I don't remember doing this one. Oh, 50 kilogram pole vaulter running at 10 meters per second goes over the bar. At 1 meters per second, how high was the jump? Okay. So, first of all, a pole vaulter is not going to run 10 meters per second. That's like Usain Bolt fast, and you're not going to do that with a pole. But if you did, your kinetic energy's there. We're ignoring, in this problem, the elastic potential energy you're storing in it as you're driving the pole in. There's no way to calculate that, and they didn't consider that when they wrote the problem. But you got gravitational potential energy plus some kinetic as you go over. So your total mechanical energy before and after is the same. It's all kinetic at first. It's mostly gravitational in the second part, but you got a little bit of speed, so you got a little bit of kinetic. So if you go 1/2 mv squared equals mg plus 1/2 mv squared, you have everything but h. Solve h, and it comes out to be 5.0 meters. The next one, 37 or 31, it's easiest to do this way, and I think the book answer on this one is wrong. 31. Yeah, they come up with 10.2 meters and it's not. If you're gonna take a 1/4 kilogram mass and push it with a spring down and let it go, when you push it down, well, first of all, mechanical energy is conserved. So whatever kinetic and potential energy you had to start with is equal to the kinetic and all the potentials you have to end with. We don't even really need the kinetic in here, because when you push this guy down, you are going to do the work to push that down and latch it. Gravity's not going to do any of that. And I don't think they took that into consideration when they wrote the problem. It's not like gravity does the work down and then gravity does the work down. You're going to do the work to push it down. So when it gets down to the bottom and you release it, it's got elastic there. But when it comes up this far, that's going to eat some gravitational potential energy up, which you have to subtract off or add and keep your G negative. And then it's going to go MGH up from there. So I don't think they subtracted this little term off when they did that problem. But if you put the 1/2 kx squared that you push down 0.1 meters and store that energy, and you subtract off that little bit of gravitational potential energy, I'm going to call this x because it's 1/2 kx squared to push that down. So if that goes down x, it's going to come up the same distance. And we'll call that x instead of h like this one. H is from where it's released up. Above the point of release, I'm going to call the point of release here. Or maybe they're calling the point of release here, but I'm going to call it here. I don't know. You get the idea. If you could solve it one of those two ways, I'd be happy with it. And then it would go up however high, and I come up with 10 point. Actually, it will be 10.2 meters, because if you call this the point of release, yeah, then you're adding in, here we go. So maybe they do have it right. Your 10.1 meters plus your 0.1 meters for x is 10.2 meters. Okay, and then on the next one, wants to know why a satellite basically doesn't slope. What's this say? What does the work energy theorem predict about the satellite's speed? That it should be 0 and there's no work done on the satellite because your distance to the center of the Earth doesn't change it, and that's where your gravity is calculated this way. It's g times m times the integral of 1/r dr, where a radius is the distance from the center of the Earth to wherever your height is, and that doesn't change. So if the distance is 0, I know the force is there, that's what we got right here, but the distance is 0, change. So you're doing no more work than these people are doing. When they're walking across this savannah or whatever this is, they've got a force, but they're not doing work. It's very efficient, by the way, to carry containers this way. Which, think about it, is walking a good form of exercise? Oh, walking's great exercise. Well, compared to laying on the couch eating chips, yes, I'll agree with you. However, you don't have any force you've moved. If you want to exercise, walk or climb stairs. That'll really get your heart rate up. But the problem is, of walking, we're real efficient. You know, basically, you're going a distance, but you're not applying a force distance. Or put a big tire on behind you and tie it to you and drag a tire up and down the hallway. Do work that way. Then you got your distance going this way and a force going this way. But when you're walking for exercise, you're not exerting a force this way. If you're exerting a force this way, you're not exerting a distance this way. They got to be in the same direction, not perpendicular. Here's the one I like. You got a diver and the diver jumps into the water and slows down over 5 meters in the water, we want to know what this force is. Well, the book did this one wrong because there was something obvious but not obvious that they forgot. They are calculating the gravitational potential energy from all the way up here, 10 meters above the water, to all the way down here, 5 meters below. But they forgot one basic thing. When you go in the water has about the same density you do, and it's got a buoyant force, so it's not applying that force through here. It's only applying resistance. So you can only calculate that part. I'm gonna have to stop the tape and think about that one. So your gravitational potential energy is calculated from here to here, because once you get in the water, you're neutrally buoyant. Roughly. It depends on your density. And then the work that's done is just from here to here to stop you. So it's as simple as 50 times 9.81 times 10 meters times the force times 5 meters.